Hello. I am Andrew Corkin. In this video, how I made a table hockey robot, I will tell you how I connected the stepper motors to the Arduino controller, and how to achieve speed, parallel operation, cooling, and silence from the stepper motors. The internet mainly discusses the use of stepper motors, in 3D printers, CNCs, in a robotic arm, with 6 degrees of freedom, and similar devices. But I need to move the player 40 centimeters in a split second, or hit the hockey stick on the puck, so that it flies into the goal, through the entire playing field. And what to do: set up experiments, and squeeze out all power, from the motors. The stepper motor shaft rotates with pulses, and the motors, that I used for the robot, Nema size 17, make one full revolution in 200 steps, 1.8 degrees per one step. I purchased the most common drivers for A4988 stepper motors, bought an Arduino Mega controller, with the largest number of inputs, outputs, CNC Shield version 3 for conveniently placing 4 drivers at once, a 12-volt power supply, connected everything according to instructions from numerous sites. I figured out how to write a sketch program for Arduino and ran it. The motors began to spin, but I needed speed. It turned out that if you apply 1000 pulses per second, from the controller to the motor will rotate at a speed of 5 revolutions per second. Great, but that was not enough. Increase the number of pulses, and the motor stopped moving, it beeps and does not go. There is not enough strength to start immediately, at such speeds. It's like on a machine with mechanics to immediately engage 5th gear. I had to modify the sketch of the controller, for a smooth, but if possible, quick start. I made my own class for a smooth start, in which I use the cubic parabola formula, with additional coefficients. At first, the intervals between pulses need to be done more so that the motor starts moving, and then smoothly reduce the intervals between pulses. The motor will smoothly accelerate thanks to such a program variator. For different motors, there may be their own conditions. For accelerating as quickly as possible, you need to experiment to understand where the ceiling of the motor's capabilities in voltage and current is. With this overclocking, there are always missing steps, but the loss of several steps, for the purposes that I pursued, is not important. This is not 3D printing. To summarize, for maximum RPM, you need to ensure smooth acceleration. The robot uses 12 stepper motors. This array of motors is controlled through one Arduino Mega controller, which was selected due to the presence of a large number of pins, inputs, outputs. To control 12 motors you need 12 pins for transferring steps from the controller to the motor driver, 12 pins for setting the direction of rotation from the controller to the motor driver, 12 pins to control on/off motor driver, optional, but desirable, as it turned out to be important for cooling. An additional 24 pins are involved. 12 pins for receiving data from optical limit switches, for the safety of mechanics, limiting the area of movement of player drives. Can you really trust the program? Sensors are installed one at the beginning and end of each drive, and there are still springs for soft stop. Can you really trust sensors? 12 pins for RGB LEDs indicating operating modes, green on when power is applied, blue is added when moving forward, back, and red is added when the hockey stick is rotating. In general, green for useful, blue and red for beauty. The computer sends control commands via the USB port to the Arduino controller, and here you need the ability to work all 12 motors simultaneously. In practice, during the game, I did not see that all 12 motors worked at the same time, maybe 4, but this is technically provided. The brain of the robot is now in the desktop computer, as a temporary solution, until it moves to the microcomputer aboard the robot. The Arduino Mega controller is equipped with a large number of inputs, outputs. If you need to solve a certain problem, you can connect dozens of stepper motors. If the stepper motor driver is energized to the VMOT pin, and the driver is turned on, by default enable is 0. So it turned on, the motor may start to squeak a little, depending on the driver. and the motor windings, and the driver will start to heat up. You can touch the driver heatsink, and make sure of this. I started using the power of the 12 volts motor, and quickly felt the heat, but at 36 volts I really did not like this effect. I did not wait until the motor windings burned down, or the driver burned, and began to figure out what was wrong. It was the enable pin. If rotation of the motor is not required, turn off the driver, and when rotation is needed, you just need to turn on the driver. Since the robot uses 12 motors, and they do not rotate at the same time very often, it means that they can be allowed to cool when they are not needed. I took control the enable pin of each motor driver through the Arduino controller. It took an additional 12 pins to use the controller, but the drivers became cold and the motors no longer make noise, although 36 volts is used. First, I purchased drivers for the A4988 stepper motors. It took 12 pieces. They are popular, reliable, simple and straightforward, as well as very cheap. For beginners it is. Everything worked almost well. With steps everything is clear. 1 impulse is 1 step, 200 impulses at 1.8 degrees per 1 step is 1 revolution of the motor. There were 2 unpleasant moments. At low revs, especially when you need to slowly turn the player's stick, tremors set in at the motors. And yet, this squeak. When 12 motors were running, it felt like R2-D2 was talking to me. I began to look for a solution to the problem and found out about quiet drivers with German Trinamic DMC 2100, 2130, 2208 chips and other series. They cost several times more, but if you need silent and smooth rotation, they are worth it. TMC has a stealth chop mode with interpolation of 4 or 16 input pulses into 256 microsteps. After testing, I chose the 4 to 256 microsteps mode, as I use Arduino Mega 2560 16 MHz and this controller was no longer able to issue the required number of pulses for the 16 to 256 mode. The sketch for Arduino needed to be added a little, since now for a full revolution of the motor it was required not 200 steps, but 4 times more, 800 per 1 full revolution, due to the stealth chop 4 to 256 mode used. More steps, so more smoother and quieter move. I had to work a little more with a soldering iron under a magnifying glass to turn on the TMC 2100 driver the desired mode 4 to 256 through the jumpers. It turned out that the drivers in China did not connect the pins of the Trinamic chip and the MS1 and MS2 legs. But, it was worth it. The rotation is now smooth and silent. I hope my experience is useful to someone in other projects. In the next video, about assembling my robot, I will tell you how I tried to score the first goal, and the first drive began to move. You will be interested.